this is the last lecture on the class of this high temperature ceramics, and in this lecture I will describe the erosion wear of niobium diboride ceramic. So, like titanium diboride, niobium diboride is also one of the ultra high temperature ceramics, and number of groups around the world are working on this ultra high temperature ceramics. So, that is why what we call global scenario on ultra high temperature ceramics research. You will see in US it is Bill Farnell's group at Missouri Rolla, Van der Paris group at Imperial College London, and Bill Lee and John Wiener, and in Europe also in Italy some of the groups are working. In India it is Biswas's group and Vikram Jairam's group at IISc Bangalore, apart from the 2 instructors of the present NPTEL course, and in Japan and China a host of people are working at NIMS Tsukuba, Uyakoma National University, Tokyo Tech, HIT China, as well as some people in Korea. They are working also in ultra high temperature ceramics. So, this is the broad overview of ultra high temperature ceramics in India, and as you see that several IITs they are working in ultra high temperature ceramics. Out of them very few groups are also working on tribology of ceramics. Particularly the tribological properties I can mention that VSSC Trivandrum, this is that ISC Bangalore, for example this DMRL Hyderabad, CGCRI Calcutta, IIT Kharagpur, IIT Roorkee, IIT Kanpur. These are the places where tribology research is currently concentrated. Now, niobium boride is one of the member of this transition metal borides, and then you can see this transition metal borides, this consolidation of transition metal borides like titanium diboride, zirconium diboride. The similar challenges exist also for niobium boride. So, first thing is to start with these starting powders. In the niobium boride, for example, if you see in the top panel A figure, it is that unmilled powder, and in the B figure it is for the B, C, D is it that after ball milling for 16 hours with tungsten carbide. This is for tungsten carbide, this is for agate, and this is for zirconia. So, only in case of zirconia you see that D90 is 713 nanometer and D50 is 4991 nanometer. In agate apparently the D50 values is fairly low, that is 171 nanometer, but there is lot of contamination from agate, as you will see later. Now, if you see that X-ray patterns, X-ray diffraction patterns, you will see that the contamination from silica is quite extensive here in the silica, and then tungsten carbide milling by media also there are small amount of tungsten carbide are present, and niobium boride is quite significant in all these cases. Now, as far as the sintering and densification is concerned, at 1750 degrees Celsius, if you see niobium boride after spark plasma sintering, it is sintered to 99.5% sinter density. Now, spark plasma sintering is a technique which is very similar to hot pressing, but the fundamental difference between spark plasma sintering and hot pressing here, it is the current that is passing through from the top die to the bottom die through the graphite die punch assembly, which contains these ceramic powders. And since it is a porous ceramic powders, there are a lot of void spaces. Now, when current is trying to pass through these powder particles, and if the powder particles are non-conducting, that majority of the current will pass through the graphite die wall. But here some more current will be passing through the powder compact, and what happens that in case of the powder compact, that void spaces there, the current will experience resistance, and because of the resistive heating and Joule heating, that locally the temperature will shoot very high, leading to the higher mass transport. That is the entire mechanism of the spark plasma sintering of the ceramics. Now, what is the spatial processing scheme or heating scheme that we have utilized to densify this niobium boride materials? So, we heat it up to 1500 degrees Celsius at 100 degrees Celsius per minute heating rate, and then we hold it at 5 minutes. At 1600 degrees Celsius we hold it at 5 minutes, at 1700 we hold it at 5 minutes, and finally 1750 degrees we hold it for 2 minutes. So, it is a 4-stage sintering, or what we call multi-stage sintering, where the powder compact was held at 1500, at 1600, at 1700 degrees Celsius for 5 minutes each, before it is held at final sintering temperature 1750 degrees Celsius for 2 minutes before it is cooled to room temperature. And what you notice here, when it is part plasma sintered at 1750 degrees Celsius, this niobium boride with zirconia milled powder, you can see there is a clear presence of the tetragonal zirconia. But when you use as a agate as a ball mill, then what happens, there is a second phase, then this is apart from silica there is a third phase called niobium Nb-B2. So, what happens, the niobium oxide, niobium boride reacts with silica, and then it forms this Nb-B2, and then also it will form this boron oxide. Okay. So, this reaction essentially take place during the spark plasma sintering of these materials. So, this is that Hadouf image. So, high angle annular diffraction pattern images, TM bright field micrograph. So, what you see here, that there are presence of niobium boride, and also zirconia phase is dispersed in the matrix, and there is a equiaxed grains of this niobium boride, which if you look at this micron bar, it is roughly around 1 micron in size. So, 1 micron or less than 1 micron, and this is that selected area diffraction pattern of the hexagonal niobium boride, and where it is very clear this niobium boride is retained along with zirconia. Now, in terms of the different properties, for example, sinter density, niobium boride has a sinter density of 6.55, while theoretical density is 6.58, it is close to sinter density. Hardness is 21.7 gigapascal, which is very high. Elastic modulus is 4015 plus 9.1 gigapascal. Fracture toughness is 4.4 MPa square root meter, and tensile strength is 88.73, 88.3 megapascal, and flexural strength is around 600 megapascal, which is this combination of properties is not bad. Now, what you notice here, there is a very clean grain boundaries. So, no grain boundary phases, that is also expected, and then we have seen the stacking faults and some part of these twins, and these are these twins, they are intersecting twins are observed in these materials, and these are the kind of defect structures which we have very clearly observed in this niobium boride microstructure. This is the high resolution transmission electron microscopic images, and this one is essentially called lattice fringe images. So, this transmission electron microscopy analysis of ceramic materials just like niobium boride and so on is extremely difficult, because the sample preparation itself, it takes a lot of time in, because one needs to have that electron transparent thin film before one can get very decent, reasonable and scientifically meaningful transmission electron microscopic images. Now, this left one, if you see, this is this bright field TM images, and bright field TM images of niobium boride, one can clearly see these lattice fringes, right. Now, in the right hand side of the images, you see that FFT images as well as inverse FFT images, and these from these FFT images one can find out that what is the interplanar spacing. In case of hexagonal niobium boride, the interplanar spacing is 0.325 nanometer, and you will also see a positive edge dislocations. While you see the different lattice planes, also you will see there is a planar defect, like in the terms of the edge dislocations, which is a line defect, which are also present in these materials. So, this is another bright field images showing the Moiré fringes as well as the asymmetric twins. So, these asymmetric twins essentially indicate that when these materials are heated at high temperature under uniaxial compaction, so essentially deformation twins also generates, particularly at high temperature and when it is cooled down. So, these twins are present across the grains, which is the way it should be, because once a twin starts, it does not terminate, it should not terminate at the middle of the grain unless it is intersected by another advancing twins. So, that is what we learned in the standard material science textbook, and we also observed the same phenomena in case of ceramics. Now, coming to the high temperature erosion behavior. Now, before I explain you that high temperature erosion behavior. So, erosion essentially means that you have a flat surface, right, and you have a erodent particle. So, this is called erodent particles. So, which will be impinging at an angle theta, right, and this what it does is this erodent will strike the material and a stream of erodents, right, at a particular speed, and this erodent depending on the erodent type and velocity, this flat material would experience a wear and they will form the crater subsurface deformation here, and this particular erosion wear loss in case of metals you can find out by measuring the changes in the weight. But in case of ceramics, just like any other case of ceramic materials, we use laser surface profilometer, we take different 2D profiles, then we integrate over the distance to get the wear volume. Now, if you plot the erosion wear rate as a function of angle of impingement, that is theta, then what happens in case of metals, it goes through a it goes through a transition at around 30 to 40 degree to theta values, and in case of ceramics, then this is for ceramics, okay, it goes on increasing up to the angle 90 degree, okay, and this is the case for the metals, and this is the case for the ceramics. So, for ceramics erosion wear is maximum at 90 degree. So, therefore, what is the point that I am trying to make here is that when you do the erosion wear experiments with metals, but you should conduct these experiments preferably at 30 to 40 degree, because one of the major reason behind that, because you know that 30 to 40 degree erosion wear is the largest, or erosion wear goes through maximum, and one has to, when you develop new materials for wear resistance applications, it is important and imperative to understand their wear mechanism and also measure their wear loss at the most aggressive wear conditions as much as possible. So, from that point of view, for ceramics, that angle of impingement should be 90 degree for to assess the wear resistance under the most aggressive conditions, and that is at the impingement angle 30 to 40 degree for metals. Although people do vary the angle of impingement, but if you want to do very limited experiments and just to assess the performance under the most aggressive erosion wear conditions, then I would suggest you to do it where the wear loss is maximum. So, what are the different parameters that is important? What I said, that erodent type, typically the erodent type can be either alumina or silicon carbide. This is the most commonly used erodent. Then erodent velocity, that velocity at which the erodent is impinging, and what is the kinetic energy of the erodent? It is half mv square, right. So, m is the total mass of the erodent, v is the velocity of the erodent. So, half mv square is the kinetic energy, and kinetic energy that will be transferred to the material, and that can cause either deformation like in case of ductile metals, or it can cause fracture in case of brittle materials. So, these are the two major mechanisms that can be operative under the for the two different classes of materials. Okay. And third one is the temperature. Temperature means particularly for ultra high temperature ceramics, one must do erosion study not only room temperature, but also high temperature as high as possible like 800 degree, 1000 degree and so on. Here I must mention that most of the commercial machines at present are limited in terms of their capability to operate as high as at 1000 degrees Celsius. So, there should be a push for all the commercial suppliers to design and develop new erosion wear tester or new tribo tester with their capability to work at 1000 degrees Celsius and beyond. So, higher the temperature capability, more would be our understanding of the high temperature erosion or wear at height of different ultra high temperature ceramic materials. Now, having said this, we have done these experiments in that gas jet erosion setup. This is the schematic of the gas jet erosion setup. So, this is the furnace. So, you have to keep this entire erosion nozzle as well as the specimen holder inside the furnace here. So, this is the typical nozzle length and this is the standoff distance, and this is the mixing chamber. Mixing chamber is like, when you want to use two different erodent powders, you can mix it at intermediate place, and you can mix also with the gas, and through this gas jet these erodent particles will be bombarding on the material surfaces, and when materials will be experiencing very high temperature. And through nozzle you can also tailor that depending on the nozzle diameter, you can also allow the amount of the erodent passing through this nozzle diameter. Okay. So, this is that 15 millimeter diameter samples typically we use, that is the top panel. You can see that sample holder that is embedded in the sample holder, and this is at 25 degrees Celsius. You can see through the glass that this erosion experiments, and when the sample is red hot at 800 degrees Celsius, this sample also this erosion wear is possible. Erosion experiments can be conducted at 800 degrees Celsius as well. Okay. This is the optical profilometer based surface analysis, 2D surface analysis at different temperature from at 25 degrees Celsius to 400 degrees Celsius to 800 degrees Celsius, and what you notice here in that 25 degrees Celsius it is 29.8 micron, in 400 degrees Celsius it is 12 micron, and at 800 degrees Celsius it is 8.3 micron. So, if you increase the temperature, if this temperature is increases of the erosion, if you see that erosion wear depth, that micron value decreases. So, what it means that severity of the erosion damage that decreases as you increase the temperature, and this is an extremely important observations, because these ceramics are meant to be used for high temperature applications, and if these materials can experience less wear or less erosion damage at high temperature, there is nothing like it, and that is how this there is a success in developing this kind of materials with the expectation that these materials would experience less wear at higher temperature. Now, in terms of the phase assemblage after erosion test, what you can see is that this niobium boride materials, this is the niobium boride material, and you can see at 400 degrees Celsius very clear niobium boride peaks, there is no niobium oxide peak. So, niobium boride is extremely resistant to oxidation. At 800 degrees Celsius you will see a lot of these alumina particles, they are kind of completely embedded on the or covering the surfaces, that is why you get lot of alumina particles. So, perhaps at higher the temperature, these alumina particles almost like they are welded on the material surfaces, and that is why you are getting this alumina peak very strong. And tetragonal zirconia peak, that is present in the spark plasma, spark plasma sintered materials, and that comes from the milling media for these particular cases. Now, as I said that as a material scientist who have who have great interest in tribology, we are always interested to see how these wear mechanisms they changes at different temperature, right. So, this one has room temperature at 25 degree room temperature, and this one is a 400 degree Celsius. So, at room temperature you can see there are signatures of this flaky exfoliation, as well as there are small cracks, and these small cracks you can see very easily. These cracks are present, but at 400 degree Celsius, after the erosion test is over, you can see there are signature of the pull out. This is the circle, the way I am tracing. This is the circle for the grain pull out region, and there are sharp and shiny fracture edges that are also clearly observed after testing at 400 degree Celsius. That 800 degree Celsius, you remember that at if you remember that wire read that at 25 degree, if at room temperature it goes to 400 800, the wear depth decreases, and what it means that either these alumina particles are covering entire material surfaces, and then even after ultrasonic cleaning also these alumina particles are embedded very strongly. And the second thing is that perhaps this at 800 degree Celsius at higher temperature, the ceramic is not prone to brittle fracture anymore, because at high temperature there may be signature of some deformation that is possible. And that is why this grain pull out and fracture edges, although they are observed, but the severity of wear is certainly lesser than in the room temperature or 400 degree Celsius. Now, what we have done, and that is quite interesting, is that we have to understand that what is the wear mechanisms in with much more clarity. In order to do that, we have taken that eroded surface and this that debris particles, and then we have done very careful TM sample for just we put it in the grid, and then we have milled it, and then what we have done the transmission of the microscopy images. What you see that most of the cases where there is niobium boride is there, but there is also orthorhombic zirconia. So, this orthorhombic zirconia was not present initially, it was all tetragonal zirconia. Now, as I said, we have seen for the cryogenic sliding wear of zirconia, where tetragonal zirconia goes to orthorhombic zirconia, and before it goes to monoclinic zirconia. When tetragonal zirconia undergoes phase transformations, the orthorhombic zirconia is the intermediate phase. So, orthorhombic zirconia phases present not only at low temperature sliding conditions, cryogenic sliding conditions, but also when these materials are eroded at high temperature like 800 degree Celsius, again tetragonal zirconia transforms to orthorhombic zirconia, and very confirmatory evidence we have got it from selected area diffraction pattern, and this is what you can see here, that is SADP pattern of this orthorhombic zirconia. Now, when you see this eroded surface, in that left hand image you can see the bright field image of this ultra fine scale microstructure of eroded surface, the surface scratches and so on, and you can see there is also signature of niobium oxide formation. Now, this niobium oxide formation is so low that one cannot record using X-ray diffraction pattern, and they are because their intensity or their amount is much less than what can be detected using X-ray diffraction analysis. But here what we can see here, that in the selected area diffraction pattern clearly shows that Nb-205 has formed, and Nb-205 essentially is the result of so niobium oxide, so niobium boride Nb-B2, it undergoes oxidation to Nb-205 during the erosion wear at 800 degree Celsius. And you see that Nb-205 is a monoclinic phase, and this Nb-205 also lattice spacing is 4.489 nanometer. And if you look at the right hand images, you see there is a bunch of edge dislocations, and these edge dislocations are positive and negative edge dislocations. At some of the places positive and negative edge dislocations that has come together, and then they can annihilate, and they can form a very clear lattice plane. So, what is the major message that we are getting in this after this erosion? Because this is the extremely important observations, because we have done this erosion where at different temperature at 400 degrees Celsius and 800 degrees Celsius, and we have done this careful transmission electron microscopy image analysis. And what is most interesting, that whatever we are not able to detect using X-ray diffraction or scanning electron microscopy, when you do transmission electron microscopy, we are able to see all those signatures, like Nb-B2 undergoes oxidation to Nb2O5 grains, and that is because of the erosion. You also see there are lot of dislocation activity in this eroded region, essentially saying that these are the signs of dislocation plasticity, which is taking place at high temperature, leading to the reduction in the wear damage, wear induced damage. So, this presence of these multiple dislocations, if you look at this particular micrograph, you know that in this kind of images for the Nb2O5 grains, it is extremely fascinating to see that these particular grains is this Nb2O5, these are the 2 grains. Here the along the 313 bar plane, the interplanar spacing is 0.309 nanometer, and here 010 plane, here the Nb2O5, the interplanar distance is 0.382 nanometer. So, in this particular range, you can see that there are lines along this line, this edge dislocation, and these edge dislocations essentially are present, and they are the signatures of the dislocation activity in these materials of the eroded surface. So, all in all, this combination of the dislocation activity as well as Nb2O5 phase formation essentially indicates this erosion experiments at 800 degrees Celsius causes measurable oxidation and also noticeable dislocation activity, and it is quite plausible that dislocation plasticity reduces the wear of these materials, because dislocation plasticity, in contrast to micro cracking induced spalling, which commonly takes place in the case of the brittle ceramics. So, these are the 2 things that is really important in this particular case of ceramics. So, finally, I would like to acknowledge the different funding agencies which have supported our research on tribology over the period of close to 2 decades now. First at IIT Kanpur, Indian Institute of Technology Kanpur, and secondly at Indian Institute of Science Bangalore. And these funding agencies, mostly they are federal government funding agencies like Department of Science and Technology, Department of Atomic Energy, Defense Research and Development Organization, and Indian Space Research Organization. And all these ultra high temperature ceramics work like zirconium boride and titanium and zirconium boride based materials are recently supported by BrahMos Aerospace, New Delhi, that is a joint Indo-Soviet venture on aerospace. Thank you very much.